All right, our next talk will be complete first-order reasoning for properties of functional programs. It's by Adithya Murali, Lucas Peña, Ranjit Jhala, and Madhusudan.
Okay, hi everyone, I'm Adithya, and today I'll be talking to you about our work on complete first-order reasoning for properties of functional programs. This is joint work with Lucas Peña, Ranjit Jhala at UCSD, and my advisor Madhu in Murali, Illinois. Now, this work goes from practice to theory. In verification of functional programs, there's a popular heuristic employed by many tools like Liquid Haskell, Leon, or Stainless for Scala programs, Daphne, etc. We undertake a foundational study of this heuristic and develop a theoretical framework to understand its effectiveness. The heuristic that I'm talking about is essentially unfolding definitions followed by SMT solving. Let's call that USMT. For those of you who know, this refers to unfolding recursive definitions, treating them like uninterpreted functions, and calling an SMT solver. We'll see an example of this later in the talk. This heuristic is very effective in practice, and like I said, many tools use it. But weirdly enough, it also fails very easily, and in fact on simple examples. For users, this can be a frustrating experience because they know that the theorem is true, and they can prove it on paper, but the tool cannot. You can't generate counterexamples because there are no counterexamples. The theorem is actually valid. And if you try to look at the internal state of a prover, it's meaningless. In this work, we ask when the heuristic works, when it fails, and more importantly, what we can do to overcome the failures. And the answer, surprisingly, turns out to lie in the completeness of a certain first-order logic over ADTs and recursive definitions. Let's just look at an example. Here we have the algebraic data types of lists over integers. We also have programs which we write as recursively defined functions. We have two functions. Insert front simply inserts the given key at the head of the list, so that's just a cons. Find is a recursively defined function that goes through the list and checks whether the given key is equal to any of the elements in the list. Now we want to show that if you try to find a key after just inserting it, then the find function will return true. How do we prove this? Well, first we unfold the definitions on the given terms. So insert front of x comma k is equal to cons k comma x. Let's call that equation 1. And then we unfold the definition of find on cons kx. Let's call that equation 2. We now ask an SMT solver whether 1 and 2 conjunction imply the property phi. Note that this is a quantifier-free formula. And of course, in this case, this formula is actually true. The relevant bit is the disjunct marked in pink. This is an example where the USMT heuristic succeeds, and many proofs are of this kind in practice. But like I said, USMT also fails on very simple examples. Let's look at such an example. We still have the same problem as before, except now we want to insert at the back of the list instead of the front. So now we have a recursively defined function called insert back, and we want to prove as before that finding after insertion returns true. Now unfolding does not work here, no matter how many times you unfold. And to see why, think about unfolding the definition, let's say 3 times. You will only be able to know from the unfolding that the list obtained after insertion is equal to the original list in the first 3 elements. So for the 5-element list shown on the slide here, you can't actually conclude from just 3 unfoldings that the property that find will return true. This is the fundamental tension that we want to study. And so I'll give you an overview of our result. So verification conditions, or VCs, for functional programs are written in a first-order logic over algebraic data types. The model where you want to check the validity of the VCs is the standard model. So that's Zeus over there. This is the standard model. So the ADT sort here is realized by an initial algebra. The integer sort is the true integers, etc. And this logic is actually incomplete, which means no procedure can prove all valid theorems. In contrast, we can also consider the class of models obtained by axiomatizing each sort. So we have other people made in the image of Zeus. We can even give a complete axiomatization for each individual sort, like ADTs, sets, or integers, and consider the models of that combined axiomatization. The standard model is one such model, but there can be many other models that respect the axiomatization. And so in the context of lists, you can think of these other models as infinite lists for today. We'll see an example of this later. In the context of this picture, the key insight is that unfolding definitions and SMT solving are both sound for the axiomatized class of models. which means that any theorem that can be proven using the USMT heuristic is actually a theorem in this weaker class of models. More importantly, we show in this work that USMT is actually complete for the theory of axiomatized models. And this helps explain why the heuristic is so effective in practice, right? Because we have very good axiomatization for the individual theories, and most theorems that people want to prove actually do follow from these axioms. But our result also helps explain why, despite this effectiveness, USMT can also fail very easily. When a theorem has to be valid in the theory of the axiomatized models, it has to hold in every axiomatized model. But this need not be true. There can be a model whose individual sorts satisfy their respective axiomatizations, but in combination, the model falsifies the theorem. We call these rogue non-standard models. So that little devil fellow over there is preventing your theorem from being provable by this heuristic. Non-standard models are actually well known in logic literature, but these are usually models that are indistinguishable from the standard model using a formula. Individual sorts have such non-standard models, and they have complete axiomatization, so this is not a problem. But their combination allows for these rogue non-standard models to exist, which can in fact falsify a theorem that's actually true on the standard model. Furthermore, our result also helps explain the role of user help when USMT fails. The user provides help in the form of inductive lemmas to bridge the gap between axiomatized models and the standard model. And a useful lemma eliminates the rogue non-standard models, thereby helping prove the theorem. With this understanding, let's look at that failure example again. We know that no matter how many times you unfold, you can always find a bigger list on which USMT cannot show the property. We can in fact generalize this intuition into a rogue non-standard model containing an infinite list. So let's just look at this infinite list 1, 2, 3, and so on. And infinite lists are actually a legitimate model of the ADTs. Do check out the paper for the detailed explanation of why that's the case. But let's just take that for a fact. And in this model, insert back can actually be interpreted in a way such that it just loses the key. It keeps recursing down the list, and then in the end, it just returns the original list. So it basically behaves like identity. And then find only returns the key if it was already there in the original list. In this model, think about inserting the key 0 into the infinite list shown here. Insert back will just lose the 0, and find will just return false. So this property does not hold. And this kind of model is why your USMT heuristic cannot prove this property. The way to overcome this failure is to actually prove the property by induction. So you assume it for tail of x, and then you show it for x. And more generally, you assume a helper lemma, you show that lemma by induction, and then use that lemma to prove the theorem. And such lemmas rule out these non-standard models. This is the formal statement of our completeness theorem. I've shown the pseudocode of the USMT algorithm on the right, where the indefinite unfolding of definitions is the 2 lines in pink. We denote the theory of the axiomatized models by T-comb for combined theories. We write the defined functions as defs, the quantifier-free property we want to prove as phi, and then the VC can be seen as checking the validity of the formula defs implies phi. We show that if this USMT algorithm returns valid, then defs implies phi is actually a theorem in the combined theories. And this is the insight that we saw earlier, that it's sound only for this weaker class of models. More importantly, if defs implies phi is indeed a valid theorem in the combined theories, then USMT will eventually prove the theorem valid. And this shows that USMT can prove precisely all the theorems in T-comb. Our theorem requires that the definitions be provably acyclic. This is actually a generalization of termination, and it essentially says that you have to prove the recursive definitions terminating using ranking functions. Every tool we know of proves programs terminating in this case, in this way, so this requirement is actually satisfied in practice. And in fact, if you look at proofs of termination in very many tools using ranking functions, you will notice that they are first-order proofs, because you can't express well-foundedness in first-order logic. That is only in the mind of the user, and you know that the standard model is well-founded. So acyclicity actually captures precisely how tools know that a certain definition is well-formed. And so a really primordial notion of well-definedness emerges from our result. Identifying this precise fragment is actually one of the main contributions of our paper, because finding such something that helps explain practice and also covers all the examples in practice took us over a year. I'll give you a glimpse of the proof. It's essentially a model construction argument. So what happens is that when unfolding fails, you have instantiated recursive definitions on a downward closed region. So in the case of our list example, this would be x, tail of x, tail of x, etc. And when unfolding fails, we have to construct a rogue non-standard model where the definitions are satisfied everywhere, right? So you've instantiated such that the definitions are satisfied on this downward closed part, which we call a computational closure. And then you want to make sure that definitions are satisfied everywhere so you can produce a real non-standard model. The key insight is that definitions can be extended beyond computational closures for these kind of well-formed computationally closed sets. And this model construction is actually fairly complex. I encourage you to check out the paper. But the basic intuition, you can think of this as this iceberg picture over here. And so that's it. We have finished our quest for a foundation for the USMT heuristic using our completeness theorem. USMT works precisely when the given theorem is valid under the combined theories and fails otherwise. And this means every failure is exactly because of a rogue non-standard model. This is actually an incredibly hard problem, right? It's incomplete, and so people, when they design heuristics, they know they can't prove everything. They're not thinking about completeness, but we find, surprisingly, that this heuristic is in fact complete, not for the real logic, but for a reasonable abstraction of it. And of course, the way to fix failures is to do inductive lemmas, which eliminate the rogue non-standard models. Now, I've been telling you this whole time that USMT is used by many tools for verifying functional programs, so let's actually look at some of these tools with the lens of our new understanding. First, we look at liquid Haskell. Liquid Haskell has a strategy called proof by logical evaluation, or PLE. It's essentially unfolding, but it just unfolds the definition once. It's in fact a little weaker than that. This is already very effective for the class of examples that liquid Haskell covers. And so, using our theory, we know that the gap can either come from insufficient unfoldings or from the gap between the axiomatized class of models and the standard model. We actually investigate the benchmarks in liquid Haskell. Ranjit, who's a collaborator on this project, helped us look at these benchmarks, and we actually find that most examples, the PLE heuristic fails, not because of insufficient unfoldings, but in fact because of the gap. And we in fact visualize some of these non-standard models, the rogue non-standard models in the paper. And of course, users use inductive lemmas to overcome failures. We also look at Leon or Stainless, which does Scala programs. There, this tool unfolds definitions indefinitely, and in fact, it asserts the contract on all recursive calls. This is in fact not the heuristic that I showed you, because you can also claim that the property is true for all smaller lists and then try to prove the property rather than just using the definition. This is a slightly more powerful heuristic, but we show in our paper that it can in fact be modeled using USMT. We show an encoding that basically reduces this to the USMT algorithm that we saw in the earlier slides. And therefore, our completeness theorem applies to tools like Leon or Stainless as well. And again, users provide inductive lemmas or induction principles to overcome failures. Now, the impact of our theory for tools like this is twofold. One, tool designers can now know that the instantiation strategy that they are using is actually complete in its horizon, which means you don't need to worry about instantiating other terms, and users can in fact be made aware of this fact. And you can design tools using complete instantiation techniques that are also thrifty in this way. Secondly, we can also give user feedback using these rogue non-standard models, helping the user understand why their heuristic has failed and helping them identify the kind of lemma that would be needed to overcome these problems. We have many more details in the paper. We actually provide a walkthrough of the full verification experience in liquid Haskell and Leon. We visualize these cursed rogue non-standard models, and we show some impossibility theorems that tell you why it's going to be hard to generalize our result. So, in summary, I have told you about a heuristic called USMT for verifying functional programs over the domain of algebraic data types and other background theories. This USMT is FO complete with respect to the axiomatizations of these sorts. The gap, therefore, in this heuristic is in precisely the gap between the standard model versus the axiomatized models. And lemmas then serve to eliminate these rogue non-standard models. This is, in fact, one of two results that we now know of this form. Earlier work by members of our team have actually shown this for the imperative program world, where the objects are in fact dynamic heaps rather than algebraic data types. And there, the appropriate form of USMT is FO complete. And the gap there is actually the gap between first order logic with least fixed point, the recursion, and first order logic. And there too, lemmas eliminate such rogue non-standard models. That's it. I'm actually on the job market, and my work identifies these creativity gaps in reasoning using logic learning. These are, in fact, creativity gaps because the tools are fundamentally limited in this way, and you do need human ingenuity to come up with these lemmas. Well, you need human ingenuity so far. Last year at OOPSLA, we have some work on the imperative program side where we synthesize lemmas using some of these rogue non-standard models, and we would like to carry this on for the functional world as well in future work. Thank you.
Great, thank you. We have time for a couple of questions. So I have a question while other people are thinking of theirs. Why is an infinite list a valid model, even though it's a rogue one?
Oh, great. So let's take your favorite axiomatization of algebraic data types. So this is a first order theory, right? So what you need is that if you destruct cons, then you get unique things. If you construct using unique things, you get a unique element. And you also want some kind of acyclicity, right? Which is that if you destruct finitely many times, for arbitrarily finitely many times, you can't get back the original element. All of this is true for infinite lists. If you take an infinite list and tack on another number, you do get a unique infinite list. If you destruct an infinite list finitely many times, you don't get back the same list. You get a kind of finite index from it. And you also, when you destruct a list, you get two unique sublists, a number and a sublist. So all your favorite axioms are actually true for infinite lists as well. And that's why it's a valid model of the ADTs.
I see. It's because there's no axiom that prevents it from being infinite, basically.
Yeah, exactly.
Okay.
No junk is actually expressed by saying that you have some axioms and it's the least model satisfying these axioms. But a first order theory can't do this.
Got it, thanks. Do you have a question?
Talk. Thanks. So you motivated your talk by saying you were going from practice to theory. Let me try to push you back to practice, right? And yeah, you mentioned that towards the end of your talk too. How would you present these? So first, can you, how do you present these rogue non-standard models to users? And you were alluding to using those to actually find out what inductive lemmas need to be proved. But I would assume that undecidability would still play some role in the discovery of lemmas. So
you mean incompleteness?
Yes.
Right. Okay.
So what's the boundary?
Okay. Yeah. So I'm going to explain. I'm going to answer your questions in order, right? So firstly, you asked how are you going to show these non-standard models to the user? Well, the cleanest answer is future work. But a better answer is that there is actually some work on visualizing a certain class of rogue non-standard models that you can in fact visualize in a cyclic way, right? So in this infinite list, 1, 2, 3, so on, I actually didn't need to give you a list of the natural numbers. I could have just given 1, 2, 3, 1, 2, 3, 1, 2, 3. And this is now a finitary object. And you can depict cycles, and you have to, of course, make sure that it respects the axioms of the ADT and so on. But there is some work, I think, maybe in the separation logic world or something like that, in kind of finding these kinds of models, and they use finite model finders to find such models. Now, whether these models are going to be intuitive for the users is another question, right? And so that's something that we have to work on in terms of actually surfacing these models. Now, in terms of lemma synthesis, because it's incomplete, any algorithm is going to fail eventually, and so lemma synthesis cannot also cover everything. In the work in which we did in the imperative world, we have a particular form of induction templates, and we do grammar-based synthesis, but even if you didn't do this, we have a particular template of induction using which we say, this is the kind of lemma we want. And there aren't finitely many induction templates for first-order logic with recursive definitions. Proofs, you can prove something in any crazy way you want. And so, yeah, the way in which we automate lemma synthesis is by looking at certain kinds of proofs. And that's one way in which incompleteness can manifest. Yeah.
All right, thank you very much.